Okay, then welcome to the last talk for today. We welcome Albrecht Klemm, who's going to talk about arithmetic and modularity of Calabi-Yau manifolds and string theory compactification.
Okay, so thank you very much for the invitation for this great conference. And since I'm the first one who wants to change the title. I want to say it's strings and arithmetic geometry and not strings and geometry. But the paper is based on a paper with Don Sage mainly, which just appeared, but had I think 10 years of making or something. So because I had to learn arithmetic geometry, and since this is a hard topic, I will start very gently and run out of time. So that's my plan. Well, I mean, you have, of course, in algebraic geometry, you have equations and you want to analyze them. And many of them are higher order, so it's not easy task to analyze them. Even so, you have many fields, many, so to say, tools. But one tool is you should shoot at this thing with any finite field and look what's happening. And basically, what is happening is you try to count the solutions. So the only thing that you have to know here is what the integers mod p are. So this is a finite field of characteristic p or order p. And here, for instance, is the problem. So you have to solve a linear equation mod mx mod n. And you know if mn is co-prime, then this has a solution. This, so to say, is the Chinese reminder problem. And that is actually almost everything that you can say about the linear equation. The next problem was addressed by Gauss, and he has good taste because this is a Calabi-Yau zerofold. If you homogenize it, it's a quadratic constraints in P1, so 2 points. And so how he solved that? So the first step you can actually do, I mean, you introduce a symbol that tells you and that gives you the value 1 if it has a solution, and it gives you the value minus 1 if it has no solution. And it turns out, and as I said, you can do this merely in yourself, it turns out that if this p is 1 mod 4, then it has a solution, and if it's 3 mod 4, then it has no solution. And otherwise you give this, so then you check the next prime, and the next prime is 2 that you still have to do by hand. And then Gauss realized something which is not trivial, is this what is called Gauss quadratic reciprocity. And he realized that there is this kind of reciprocity. And then when you also take into account that all of these are characters, so if you have a number which is not a prime here, then you can do this for the primes, and then it will give you the answer because it's a character, and also it has some periodicity that allows you not to check too many things, actually. So the answer is complete, but the problem is a little bit too simple. So the reason is that these fp, or you call it this integers mod p, are not dense enough in C to say something more interesting about C. And what you do is you consider the principal ring of a polynomial fp with coefficients in fp. So all these coefficients are in fp, or they are only integers mod p. And then you assume that this is irreducible, and then it has, of course, as many as n zeros. And all these n zeros you add to your field, and an element of a field would look like this, k equal 1 to n, and because it has n zeros. And these ak are the distinct roots, so it's all independent algebraically. And then you can also say is you consider, since it's an principal ideal ring, that this is a finite field in which you can invert. That's the way to say it, but the fields look like this. And then the strategy of arithmetic geometry is to capture all algebraic geometry from the information of the solutions over fpn. That's basically the strategy. And the people hope that if you take the limit n equal to infinity and get a lot of points in the complex plane, and then that's enough to get it all. And one can say it's mathematically spectacular successful. That's one thing that you can say. And the other thing is it is probably the most striking example of emergent geometry because, well, I realized that maybe a few of my collaborators don't want to go to pictures on a conference because they work for some secret service. So it is a way of coding. It's a way of coding the properties of a Calabi-Yau from sets of data, from property of the geometry from sets of data, and that is the program. And it's nowadays known as the Langlands programs, geometric Langlands programs. So the next thing that you can do with that is you take a smooth projective variety of dimension d, and you put all the coefficients in Q, because only then, if you insert the coordinates, these finite fields, then you can calculate. And if there are actually denominators, you just clear them. Because this is a homogeneous constraint, on the right-hand side is 0. It also works if you have no constraint, then you have to, you also can count the point quite easily. And then you look at, you set the coordinates, let's say the coordinates of your quintic, you set it into this field fpk, and you count the number of solutions. And this is this number. And then you form a generating function, as we also like in other aspects of modularity. And this is given here, and it's called the local Husserl zeta function. And then you get the first reward. I mean, you have done nothing that you cannot teach a school kid, essentially. But you get already the Betty numbers of the Calabi-Yau, of the manifold. Because Artin, Grothendieck, they used L-adic cohomology, I will say a little bit about it, to show that this is actually not a terrible function. It looks like an exponential, terrible, but it's actually a polynomial, a rational function. So, and it is so that the even cohomology goes in the bottom, that's because it's shift of 1, and the odd cohomology goes in the top of this thing. So that is the thing, and we can look into this function for simple spaces. So it turns out, if you take a Fano variety, that's too trivial. So there's nothing interesting about these guys. Everything is, the denominator has a fixed pattern, and there's no information in that. So Fanos are a little bit too trivial, or you can say all the information is in that. So that just gives the vertical Hodge diamond of this Fano. So then, the next step is you do it with an elliptic curve. So in an elliptic curve, because the middle cohomology has 2 elements, you get a polynomial of degree 2, and now you see in this polynomial of degree 2 there happens to be exactly 1 interesting coefficient for every p. And this interesting coefficient is what the Secret Service has to know in order to say what torus you are on. So here is an example for this Tananyama-Shimura conjecture, which was proven by Wiles. So it tells you, well, I mean, there's this infinite numbers, but they are all in another generating series, and the series is a series of Hecke eigenform of weight 2, and of some conductor, and the conductor is basically not immediately apparent from the geometry, but it is here is the weight, and then it says this is a cusp form, and it's also a Hecke eigenform. This is the notion of this space. So why should physicists care? Let me give you an example. So look at 2 examples. So the one example is this curve that everybody knows is a Landau-Ginzburg model, which is at the Gepner point. So it's a little special. And if you bring it to the Tate form, which is easier to actually to get these numbers out, then you will find that this F2 is of this form. So it's a product of the Riemann-Eta function and two products with some funny arguments and a square, so that it makes it weight 2. And it's also an eigenform, and the conductor turns out to be 27. So let's look at the second example, and this is this example, and it looks actually quite similar. I mean, what is the big difference here between these product of eta function of weight 2 and this product of eta function? Only the conductor is a little bit different. So what is the difference? What's the difference? So the difference is you look at the coefficients and you see for the second example, you see this pattern. So this is what your Secret Service gets. And then for the other example, you look at the, you look at this pattern, and what you see? Well, you see, first of all, you see periodicity, and you see a lot of zeros. So why is this there? So it's there because of the fact that this denominator of the Husserl zeta function factorizes. And it factorizes in a character. And this character is exactly the same reason that sometimes in Thomas talks, the transcendentality actually drops. It drops precisely because of this reason that the Husserl zeta function does drop. And that makes it, so to say, more like a quadratic equation, like a Gauss problem, instead of a problem of a Riemann of a cubic. And well, you have to know a little bit why this factors is not exactly integers, just integers here, but anyway. So now, first of all, this thing is a point of complex multiplication. Secondly, you know that the J function, which we usually use in Calabi-Yau to parameterize the space, is as an algebraic number. So it's not an arbitrary number. And now, of course, you know why you should care, because it tells you when there is a rational conformal field theory. And the reason is, if you calculate the correlation function in a rational theory from the transcendentality that they have, they cannot be the function that correspond to the to these complicated L function. It's just not possible. And well, I mean, you can get more. I mean, actually, this gives a complete modular parameterization of the surface. And this is given here. So you can actually use these two functions to write down. And what you do is you get the periods in terms of the periods of these modular forms. And these periods are rationally related to the Hecke-L functions. And the Hecke-L functions are basically generalizations of the Riemann zeta function. So if you talk about emergent values of something, is actually very similar, because what you get here is just the coefficient of this modular form. Everything else is the same. And moreover, they have the same product form over primes, and also have the same functional relations that you have for the Riemann zeta function, which of course leads to the famous Riemann hypothesis concerning the properties of primes. So a bit more concretely, you can do this now for the whole Husserl zeta function. That's called the global Husserl zeta function. You get then individual L functions and the functional relation. That is actually very important to get the zeta function at values where it doesn't make sense, in order, for instance, to regularize the conformal field theory, the normal ordering procedure. This is also there for these guys. So they give these values of the zeta function. They give a definition of their transcendentality, and they determine many things. I mean, for instance, they determine Feynman graphs for non-supersymmetric field theories. I'm happy to say that, and also for black hole scattering, whatever. So these L function values appear in this problem at special kinematic points, and also they set the general transcendentality of these Feynman integrals that you have to calculate. Well, they also give the asymptotic behavior of the Weil-Petersen metric. Kumrum asked me a question. I think at the end I can answer that. So then what's more is, well, this is really sluggish. They determine the masses of the d-branes because these are values of the periods, and it turned out that these values of the periods are given also by these L function values. And it's also clear that then you have to go at the special algebraic points to get behavior of the periods. And it also determines the non-minimal, the non-trivial minima of the flux vector. So why should physics care? I think the question is turned around is, can we afford to ignore? So that's in this spirit. I want to give you. I gave you the trivial part of this the introduction. Now I give you, so to say, the structure behind it. So first of all, there is a Frobenius automorphism. So if you take your coordinates, all your coordinates of your Calabi-Yau, let's say, to x to the p, then you can check that actually mod p, the thing still satisfy as the equation. This is just by Fermat's little theorem, so you can see that this is actually true. And so there's a huge action of the Frobenius, of these Frobenius of p. And so more general, the fixed points of the n powers of fp, they count these points. But it's, you need sort of, say, a representation of the Frobenius to actually make sense of it in the similar sense that we calculate from the Lefschetz theorem, let's say the orbifold fixed points. So that actually is the work of, as you need, so to say, a representation of this Frobenius algebra. And that is actually the work of Grothendieck, Artin, and Deligne. They constructed a version of cohomology which is called L-artic cohomology for any of these varieties, and proved that in this conjecture the following holds. So first of all, this Galois group acts on Phi. It has an induced action, acts on the completion of the space, and has an induced action on the on the homology of this space, this L-artic homology. And for K is XP, and Phi is this space that we just constructed over the FP. Then the Frobenius automorphism actually generates the Galois action topologically. And then you are done. You can now take the trace of the Frobenius action on this cohomology, and then this will give you these polynomials. So you have proven that you have these polynomials, you have proven what kind of degree they have, and you are done. The question is a little bit, is this practical? But let me say something more about the factorization. So the factorization of the polynomial is basically that at the special point of the manifold, the representation of the Galois group reduces. Then, so to say, it's clear that you have to trace over two different irreducible representations, and that makes this factorization. So you can everything explain in terms of, I mean, so to say, the mathematicians like the representation theoretic aspect, and that's this aspect here. And it's actually not clear that this corresponds to any symmetry that you can see on the manifold or not. That's an issue that's addressed in the so-called Motivik-Hodge conjecture. But anyway, there is a natural isomorphism of this funny cohomology group to the normal cohomology group, and that's why I didn't have to specify which Betti numbers I actually mean. They are the same Betti numbers. So that's one also one thing that that Deligne and his friends proved. So let me go a little bit further. So I mean, the people believe strongly that if the representation of the Galois group is the same, then the manifolds are the same. They call this a correspondence. And since they believe it so strongly, they sort of say focus on this representation of the Galois group. They forget about the manifold. They think, anyway, this is something that that is always given by that. But what's also interesting is that there is a version of relative L-adic cohomology. And the relative L-adic cohomology is basically relevant for D-branes. So when you have D-branes, then you need relative periods, and it should actually shed light. I mean, then what they showed, the mathematicians, that you get group extensions of the Galois group acting on these, for instance, on the relative periods, and this should actually shed light on the relative periods and potentially on the symmetries related to D-branes. I mean, and then finally, this field has a couple of, let's say, mysterious conjectures. They are super strange. So there is a strange interplay between the analytic behavior and the topological behavior. So, for instance, the Birch-Swinnerton-Dyer conjecture is the most famous one, but there are many ones also from Beilinson. And it says that basically the behavior of the L function at s equal 1 determines the torsion group, the rank of the torsion group. And also there is a partial result that they prove it for rank 1, Don and Gross. So, as I said, from the mathematical point of view, you put the motive in the center, and if you want to read about it, they actually do motives pure and motive mix, so they can actually also do D-branes, if you like, these people. But what is now this motivic Hodge conjecture? This basically says that there is a correspondence. I mean, the map has not to be 1-to-1, it can be many-to-1, but otherwise there should be a map between X and X check if they have the same motive. And if there is, for instance, a linear subspace here that is compatible with the Hodge structure and the Galois group, then it should be cut out by the correspondence. You will realize that is basically a version of the Hodge conjecture. So if you have the Hodge conjecture, you have your middle cohomology, and now you assign PQ values to this middle cohomology, then the Hodge conjecture says, oh, if you do that for a certain complex structure, then there should be an algebraic cycle that corresponds to that. The same conjecture was made by Tate. If you have, so to say, if the Galois group splits your homology in two pieces, then he believes that also then there should be an algebraic cycle that corresponds to that and explains it geometrically. So the rest of the talk is of course an idea that is obvious, namely apply this to Calabi-Yaus and see what information you get. And this has a history. I mean, this is not the first that people did this. So the first was actually Church-Schoen, and they discovered a new form of S4 gamma 25 in the Hasselbalch zeta function at the conifold. So that is long, long, long ago. And then there was a big effort by Candelas, De La Osa, Rodriguez, and Villegas, and they used in particular Twork's p-adic method. I don't know whether I can come to this, but then Jülich and Verrill and Meyer studied this in rigid Calabi-Yaus, and then Noriko Yui and Fernando Gouveia, they proved the modularity in the conifold fibers. And let me so to say tell you the problem here. So you have you look at one parameter Calabi-Yau because you think if this thing has a fiber, then there are geometric reasons that this thing splits, so that's not so interesting. So physically it's maybe more interesting, but for the general structure, what can happen, these one parameter families are very interesting. And so you look at this thing, and you ask yourself, this modularity conjecture that Andrew Wiles proved, what's the generalization of that? And the generalization is, okay, you look at this and you see two coefficients. There are not more than two coefficients because they are related by one of these symmetries that I told you in the beginning. And the general modularity conjecture says that these AP and BP are Hecker eigenforms of a Siegel paramodular form that has to be found. Now, unfortunately, almost nothing is known about Siegel paramodular forms. Only one particular case has been, or actually, yeah, only one example has been found, to be completely honest. So that's too difficult. So then we decided to study the situation when this thing factorizes. And this is how it factorizes at the conifold. And yeah, so now I have to say, I can basically say at the conifold it factorizes like this, and at the attractor points it factorizes like this. And we found the first attractor point in hypergeometric systems, and also many other new attractor points. Well, I mean, they are relevant for rank 2 attractor points are relevant for black holes and so on. But let me go to one slide that I like, and that is maybe gives you a certain kind of overview. I mean, it's funny. You can calculate the periods periodically, and by this periodic calculation, you get the Hasselbalch-Setter function. So you get the enumerative geometry completely from the periods, but you also get all the enumerative completely by the periods. So you don't have to count very far to say there must be some relation between these two things, but I don't know exactly what it is. So let me come to the conclusion. So this is about this Dwork deformation method, which also, by the way, helps you to find the periods, the attractor points. So let me make some concluding remarks. I mean, this transition matrix that you are now full of these algebraic values, of these L function values, they give the exact central charge of the BPS state at these attractor points. And you can also say, okay, instead of these periods, they are Hecke L function values. And then the Motivik-Hodge conjecture, we have proven it in one case. So that's basically a mathematical highlight of the paper. Here we have proven the Motivik-Hodge conjecture. And this means that we have a modular parameterization of this Calabi-Yau. And then, of course, also the matrix at the conifold is determined. And one thing maybe that Kumrum asked now, well, what's about the asymptotic of the metric at the conifold? Turns out the asymptotic of the metric of the conifold is determined just by kappa and this L function value. So that's quite amazing. And also the curvature, of course, then is here delta is the distance from the conifold. And what's also determined from that, from this L function values, is the asymptotic growth of the Wapakuma-Warfa invariance. So so let me summarize with these, so to say, partial results. I don't know, well, one has the impression there's a lot more, but there are also very concrete things. You can just calculate it. And yeah, thank you.